Hello, good evening, everyone. Welcome. This is SFU's Café Scientifique, and my name is Cynthia Henson. Thank you for joining us tonight. We'll just give it a couple more minutes and wait for more people to come into the attendee room. Again, I see lots of familiar names joining us today. Thank you so much for always hopping on these calls. We're staying virtual for now, and we're keeping this on a Zoom webinar format. And this is the our last session actually for the year, and we will resume these sessions in 2023 in January. Again, you are joining Simon Fraser University's Café Scientifique, and my name is Cynthia Henson. Thank you for joining us tonight. We will give it a minute more for more people to hop on the webinar into the attendee room. Let's give it maybe half a minute more. All right, I have 5:03 in my time, and I guess we better get started. Again, thank you so much for joining us tonight. My name is Cynthia Henson, and I will be your host for tonight. This is Simon Fraser University's Café Scientifique. For those joining us for the first time, this is a discussion series that the faculty stages, and in these sessions, we try to feature our faculty presenters to talk about their research work, and we invite the public to engage with our faculty members on discussions about those research work. This is our last session of the year, and there will be more to come in 2023. Stay tuned for more presentations. Because you have emailed us and you have registered on our Eventbrite pages, your emails were included in our mailing list, and you will surely receive information about the 2023 speaker lineup. Just a few reminders before we proceed. We will send you a feedback link after tonight's event. We do welcome some comments or suggestions that you might have about this series, and we hope to hear from you from that web survey. Also, we are happy to see lots of familiar names. I just wanted to say thank you to all the regulars who always join us each month. We try to do this series 6 to 8 sessions a year, and also a warm welcome to all of those joining us for the first time. It's also great to see lots of our community partners join us, even from beyond the Lower Mainland and even from beyond BC. Thank you. So let me begin by acknowledging that we are privileged to gather today on the unceded traditional territories of the Squamish, Tsleil-Waututh, Coquitlam, and Musqueam peoples. We thank them for having cared for these lands and waters since time out of mind, and we look forward to working with them in partnership as we continue to build this great city together. If you know whose territory you're currently on, please take a moment to reflect on this. And if you don't know whose land you're on, I encourage you to look it up and make yourself familiar with the Indigenous peoples whose land you occupy. All right, just a few house rules before I turn it over to our speaker. We do welcome questions and comments. Feel free to type those on the Q&A box. You should see that on the right-hand side of your screen, I believe, and we will try to read out everyone's questions after the presentation. Unfortunately, the chat page is turned off, but we're just leaving the Q&A box that you can access. There's also a live transcript that you can turn on if you find that convenient or helpful. And again, just a reminder for everyone, this event is being recorded. All right, so at this point, I'd like to introduce our presenter for tonight. We have an assistant professor from our Department of Statistics over at Fraser University. His presentation title is quite interesting: Astrostatistics, or Everything Old is New Again. Modern astronomy contends with complex physics, complex technology, and complex data. The result is an abundance of complex statistical challenges. Dr. Stenning's talk will focus on how new research in the exciting interdisciplinary field of astrostatistics is advancing both astronomy and statistics. Dr. David Stenning is an assistant professor at the Department of Statistics at Fraser University's Faculty of Science. His research interest is on statistical methods for the physical sciences, specifically astronomy and astrophysics. On the statistics side, Dr. Stenning utilizes complex computer simulations of astrophysical phenomena, along with modern machine learning and data science techniques to tackle challenging scientific problems. I don't want to take too much of his time. Friends, please help me welcome Dr. David Stenning. At this time, I'd like to invite David to screen share his presentation for tonight. Welcome, David.
Thank you very much for that kind introduction. So I'm just going to enter into full screen mode. Oops, that's she wanted to do it in presenter mode. Sorry about that. Slideshow. Okay, so thank you very much for that kind introduction. And as you heard, this Cafe Scientifique talk is on astrostatistics. I'm going to say what that means in a moment, but the subtitle, if you will, is Everything Old is New Again. And the reason for that is people in my field tend to think of astrostatistics as this new interdisciplinary field, and I myself am guilty of that because it's what we always say if we're applying for grants or to give talks at conferences. But if we kind of think about the history of both astronomy and statistics, one can make an argument that astrostatistics is really one of the first interdisciplinary field. And they really benefited each other when astronomy and statistics were both sort of seen as new areas of inquiry. But before delving into the history, I want to first talk a little bit about modern astronomy and the types of instruments that are collecting modern astrophysical data. So in the past couple of decades in particular, there's really been this explosion in the number of astrophysical observatories, both on Earth and based in space. And they're taking data across the entire electromagnetic spectrum, all the way from gamma rays to radio waves. And in addition, going a bit beyond that to have new ways of seeing or maybe even hearing the universe by detecting what are known as gravitational waves that I'll talk about later on in this presentation. And so the complexity of these instruments, along with the complexities of the data that they're generating, are leading to new opportunities for statisticians. And this is really because astronomy and astrophysics is becoming much more of a data-driven science with digital data, as opposed to a strictly theoretical or a strictly analog observational science. And so this is leading to new challenges, but also opportunities for astronomy, which is that in some sense, there's too much data. So the traditional techniques, the traditional statistical techniques in particular that have been used are inadequate for current data volumes and the data being produced by current observatories, either due to the total amount of data or the complexities and intricacies of that data. And so this is really leading to opportunities for statisticians and data scientists, such as myself, to collaborate with astronomers and astrophysicists to develop techniques that are motivated by these interesting and complex challenges in astronomy, to develop new statistical techniques suited to the particular applications at hand that might then be generalized to other kinds of applications outside of just astronomy and astrophysics. So before getting into some examples from my own research of particular areas of astronomy that has led to innovation in statistics, I should first say a little bit about what is astrostatistics, because that's not a very common term. So loosely, we can say that astrostatistics is maybe what you would expect. It's astronomy or astrophysics plus statistics. So it's a portmanteau of these two terms. So as I mentioned earlier, modern astronomy and astrophysics contends with complex instruments, complex data, and complex scientific questions. And so astrostatistics, as a general field, seeks to assist in answering these science questions by developing statistical methodology that addresses the unique challenges of astrophysical data and instrumentation. So as a statistician or an astrostatistician, it's my role to talk to and collaborate with subject matter experts, with scientists, with astronomers and astrophysicists to develop these statistical and computational techniques. And because up until maybe 20 or at most 30 years ago, astronomy wasn't as much of a data-driven discipline, or astrophysics wasn't as much of a data-driven discipline, people always comment that this is an exciting but young and or emerging or developing interdisciplinary field. But if we kind of go back a little bit to the history of astronomy, which I'll try to argue is also a bit of a brief history of astrostatistics, then we'll see that in some ways, astrostatistics is an old field, an old interdisciplinary field that we're in some sense rediscovering. So as long ago as 1500 BCE, priests in Babylon and Egypt studied the motion of the heavens, so stars, planets, the moon, any what they would have termed heavenly bodies, in order to learn something about the natural world that had an immediate purpose, which was to know when to plant and harvest crops, and also to develop a calendar. So we kind of take it for granted that we know how long a year is, and we can develop a calendar. But this was, in a lot of ways, a long-standing scientific challenge, is to say how long a day is, how long a year is. And this was important for these older cultures because they needed to know when to plant and harvest. So if they had a more accurate calendar, they could have better crop yields. And so these priests, and they were often priests at the time, would study the heavens and try to collect and analyze data in order to learn about natural phenomena. So one definition of statistics, and I won't say it's the only definition of statistics, but one definition that I like is that we can consider statistics to be the science of collecting and analyzing data in order to classify and predict natural phenomena, as well as to quantify, understand, and interpret uncertainty. So if we have this definition of statistics, then in some sense, the Babylonian and Egyptian priests were acting almost as proto-astrostatisticians because they were collecting data about the heavens, about the motion of the stars and planets, in order to predict when they should plant their crops, when there might have been eclipses, and so on and so forth. And so if we jump now forward in time, then about 150 BCE, Hipparchus used basic statistics to calculate the precession of the equinoxes and refine the Greek calendar. And it's kind of amazing because in some ways, for the time, Hipparchus's estimate of the length of a year was extremely accurate. So it was accurate to about 6 minutes, which is very impressive when you consider the quality of the data that existed at the time. So this wasn't using what we would kind of think of as current statistics. It was by no means sophisticated, but using simple concepts such as an average or a median. So Hipparchus also used statistics along with trigonometry, which was a discipline of mathematics that he founded, to calculate the median distance to both the sun and the moon. And his estimate of the distance to the moon differed from the true value by less than 1%, which is, again, kind of incredible when you think about the quality of the data that would have existed at the time, plus the fact that he needed to invent kind of an entire subset of mathematics just to be able to perform this calculation. So this wasn't using sophisticated statistics, but rather still incorporating the idea that if we take data or measure a property of the heavens, or if we record observations, that we can use a summary of these observations, such as a mean, an average, or a median, in order to obtain better measurements, better estimates of a particular quantity, such as the distance to the sun or the moon. I'll say the distance to the sun wasn't as good as the distance to the moon due to incorrect assumptions about the solar system. So if we jump in time a bit, then we start to see more sophisticated statistical methodologies being developed. And in particular, they were developed with the goal of aiding astronomical inquiry, so inquiry into astronomy. So in the 16th to 17th centuries, Galileo was sort of the first person. Some people might argue that this is apocryphal, but is commonly accepted as the first scientist to use the telescope for the purpose of scientific inquiry, specifically astronomy. So the telescope was developed as a military instrument to see ships that might be approaching or enemies that might be approaching from a distance. And Galileo, even if he wasn't the first, was one of the first people to think, what if we take this thing and point it at the sky and see what we can observe? So he did that, and he recorded observations, and he sort of used his incredible scientific intellect to reason that what he was measuring would be subject to error. So if he took a measurement of the position of certain stars or planets or the moons of Jupiter, he kind of made an argument to himself that these measurements wouldn't be perfect, but that if he were to take the same measurement again, it might differ a little bit due to maybe how stable he can make the telescope, or the atmosphere, what the viewing conditions are on a particular night, and so on and so forth. So he proposed that there were measurement errors associated with his observations, and that also these measurement errors were symmetric, meaning that they were as likely to be, a measurement was as likely to be less than the true value as it were to be greater than the true value. So in that sense, it's symmetric. So he wouldn't be either always measuring a particular property to be lower than its true value or higher than its true value. And he also asserted that the average of these errors would be 0, and that larger errors would occur less often than smaller errors. And so if you know anything about statistics, then what Galileo was sort of doing is reasoning about the concept of a normal distribution. Another name for this distribution is a bell curve. So when people talk about a bell curve, meaning more values occurring near the mean than as if you go farther away from the average value, then Galileo was making an argument that measurement errors should have this sort of a bell curve distribution that we may be familiar with. So even though this concept didn't exist until much later in the 18th century, Galileo sort of intuited its existence and used this reasoning when he was developing his concept of the scientific method. And around the same time, a contemporary of Galileo, Kepler, developed an elliptical model for the orbit of Mars around the sun. And this model was based on a noisy, unevenly spaced time series. So these are going to be measurements over time that are going to be subject to error. And unevenly spaced means that they're not taken at sort of even time increments. So they're not taken every hour or every day or every year, but rather have uneven distributions in the time spacing. And if there's any statisticians in the audience, you might know that noisy, unevenly spaced time series remains a challenge even for modern statistics. So Kepler kind of by hand took 2 years to develop a model that supported the theory that the Earth revolves around the sun rather than vice versa, and that these orbits of the planets are elliptical. So this was sort of an extraordinary achievement in what we might consider statistical model selection, fitting, and refinement, despite the lack of a proper statistical methodology existing at the time. So you had these sort of scientists developing or implementing sort of very rudimentary statistical procedures for the purpose of solving challenges in astronomy, even though they didn't kind of formalize those statistics. But they sort of used intuitive ideas that, such as if you have measurements that you believe have error, that your model, in this case, the orbit of the planet, should kind of go through the middle of those errors, the middle of those distributions. There was also, Kepler also kind of used a notion based on parsimony that a simpler model should be preferred over a model that's more complex, which is an idea that we have in statistics to this day. So if we have 2 competing models and they can both equally predict the same set of observations, then the more complex model, the one that has more parameters, the more things that we want to tune in the model. The one that's more complex should be less preferred than the model that's simpler if they both do an equivalent job of predicting future observations or explaining the current observations. And if we jump again in time now to 1795, then we get to our Carl Friedrich Gauss, who was an immense figure in mathematics and statistics and astronomy and many other areas, who I would argue is the first real or true astrostatistician, and is the reason why I say that the history of statistics is kind of inextricably tied to the history of astronomy. So Gauss in 1795 invented an early form of what's called least squares regression and the normal distribution to study the position of stars in other celestial bodies, such as the asteroid Ceres. And so least squares regression and the normal distribution are arguably two of the most important concepts in statistics. So least squares regression is a method by which we can fit a line or a curve to data. So if we have a number of observations and they're subject to measurement error, then least squares regression is how we can fit a line to those data points. And the normal distribution, as I said earlier, is this bell curve distribution. So it's the most, in some ways, the most fundamental distribution in statistics, hence the name normal distribution. And it's also known as a Gaussian distribution because Gauss was the person to develop it. And so Gauss's prediction of the average apparent location of Ceres as it came into view in 1795, as it came into view from behind the sun, can be considered the first real application of inferential statistics. And so least squares regression was developed in particular to solve this scientific problem. And so one can make the argument that the very first applied statistical methodology was developed to solve an applied problem in astronomy. So when we do astrostatistics now, that is what we're doing. We're taking problems that arise in astronomy, and we're trying to develop statistical methods to solve those problems. And like with least squares regression, we'll often find that they'll have use beyond the discipline of astronomy, even if that is where the motivation for the technique first arises. And so in this way, the birth of statistics is inextricably tied to astronomy. And as I said, we can consider Gauss to be the first quote unquote real statistician. And just to kind of demonstrate what least squares regression is, so I don't just kind of throw around statistics terms, if you've never taken a stats course, or if you understandably don't remember much from a Stat 101 course you might have taken as an undergrad or earlier, suppose that we have these four observations here, denoted by the red dots. And now we believe that these points, that a good model for these points is simply a straight line, and that these points would lie on the straight line if it weren't for measurement error. Then the idea behind least squares regression is that we want to find the line, such as this blue line here, such that if we consider the squared difference between the observations and that line, so that's denoted by the green vertical lines, we want the sum of these squared differences to be as small as possible. Hence the term least squares regression. So we take the square of the difference, so meaning we're taking the difference and we're multiplying it by itself, because we don't want the sign of the difference, whether the points lie above or below the line. We don't think that should matter. And then we're taking the sum of these squares to look at the total error in some sense. And we want to find the line determined by the intercept and the slope that minimizes the sum squared of these errors. So this is what we're doing when we're doing least squares regression. And what Gauss was doing to predict the position of the asteroid Ceres by trying to determine its orbit is a slightly more sophisticated version of this, where the model was this the orbit of Ceres instead of just a straight line, but the basic idea is the same. And so you might think that as I've only as I've gone from 1500 or so BCE up to 1795, that we would keep having more time points until we get to the present. But unfortunately, or just because of the development of the two fields of astronomy and statistics, after Gauss, they largely diverged and became separate fields. So a lot of statistics, even though the sort of fundamental tools that we use and still teach in statistics were motivated by applied problems in astronomy, after Gauss, after this time, a lot of statistics developed based on challenges arising from agriculture and biology, medicine, later on genetics, and these other areas. And astronomy kind of developed into the subdisciplines of astronomy and astrophysics, where astrophysics was more based on theory. And because the instruments, the telescopes that were used at the time, weren't as advanced as they are now, and in particular weren't producing digital data, then the kind of straightforward statistical tools such as regression were sufficient for tackling many of the challenges that were arising in astronomy. And so it wasn't really until the advent of modern computing and large digital astronomy data sets that there's been kind of a reconnection of the two fields, leading to the quote unquote new interdisciplinary field of astrostatistics that I would really argue is a reemergence of the older interdisciplinary field of astrostatistics. Hence, everything old is new again. And so the photo here is a photo of the business group of the business meeting of the Astrostatistics Interest Group from a meeting in 2018 of the joint statistical meetings held in Vancouver, BC. So this is a very tiny subset of the people who are working on astrostatistics. If you join the Astrostatistics Facebook group, you'll see that it has thousands of members. And this is because to be a modern astronomer that works with data, it really helps to be something of a data scientist or a statistician as well. So that's a little bit of a history and overview of what astrostatistics is. So for the remainder of this talk, I'll go through a few of the specific applications that I've worked on myself as an astrostatistician. So the first of these examples is in detecting Earth-like exoplanets. So first off, I should say that an exoplanet is any planet that orbits a star other than the sun, or that might be a wandering planet that was ejected out of its solar system. So we can say that it's a planet that is not orbiting our particular sun. And so this plot that we have here shows the mass of exoplanets that have been discovered, at least as of May 6, 2021. So that's given against the orbital period, so the number of days in terms of Earth days that it takes that planet to complete one revolution about its host star. So one thing that you'll notice from here, and these are confirmed exoplanets, is that if we also place where the Earth is on this diagram, that we don't really notice many planets that seem to fall where Earth seems to lie. And this is because it's very hard to detect Earth-like exoplanets, meaning planets that have a similar mass to the Earth and that have a similar orbital period. And the reason why we care about the orbital period is that if a planet has a very small orbital period, then it's likely to be very close to its host star, which would make the surface of that planet very hot. And of course, one of the motivations for searching for exoplanets, no matter how interesting it is to discover planets in and of itself, I think that there's some amount of kind of childhood excitement that comes with thinking about the fact that some of these planets could be home to alien life. And the only planet that we know of that for sure has life is the Earth. So it makes sense that we would want to find planets that are similar to the Earth. And so we can ask ourselves, why is it difficult to discover Earth-like exoplanets? So assuming that we want to find Earth-like exoplanets, what complicates this challenge? And so for that, it helps to know how exoplanets are being discovered. So there's kind of two main methods that I'll talk about in turn, the first of which is the transit method. So telescopes such as the Kepler Space Telescope will use the transit method. So if the telescope is pointing at this star, it'll measure the brightness of this star, indicated over here. And it'll measure the brightness, the amount of light over time. And so as the planet passes in front of the star, we don't often kind of see the planet directly because planets are very tiny relative to stars. But what we can see is that there's a characteristic dip in brightness that is indicative of a planet. And so this means that the planets that are easy to discover are the ones that are going to block the most amount of light of the host star as possible. And so these are going to be the planets that are both larger and closer to their host star. So a planet such as the Earth that orbits very far away from the sun and takes a full year to complete the orbit isn't going to block as much of the light. So in addition to the fact that it doesn't block as much light, we would also need to be a little bit lucky in terms of the geometry. So we would need the planet to kind of pass in front of this star in the line of sight of the telescope, and we would need to be kind of monitoring it at the right time of year. If the orbital period is something like 2 years and we're only looking at a particular patch of the sky for a few days, we might just be unlucky. And so, as I mentioned, Kepler is a NASA space telescope that over time has observed 530,506 stars and detected 2,662 exoplanets, which make up most of the planets that I showed you on that previous chart. And so it generates a lot of data because it's looking at the sky every single night. And then statistical techniques have been developed to try to detect the signal of an exoplanet. But nevertheless, that is challenging. And so most of the planets discovered are going to be ones that are big and close to their host star. Another method that is arguably in some ways more suited for finding Earth-like planets in particular and is going to be used in upcoming astrophysical instruments is called the radial velocity method. So I'll first talk about that and then talk about how we can develop statistical methods to try to find Earth-like exoplanets in particular. So the radial velocity method is also sometimes known as like the wobble method, because if you have taken high school physics, you might know that when we say that the Earth revolves around the sun, what we really mean is that both the Earth and the sun orbit the center of mass of the solar system. So if we have just a star and a planet, as we do here, as the planet orbits the star, as it revolves around the star, then the star itself is going to revolve around the center of mass of the two bodies. And what we notice here is that if we imagine our telescope as being pointed at this star, then when the star is moving towards us, the light is blue shifted. And when the star is kind of moving away from us in that line of sight, then the light is red shifted, as we see kind of in this little figure at the bottom showing the shift of the star. So this is known as the Doppler effect, and hence the radial velocity method is also known as the Doppler shift method. So Doppler shift is something that doesn't happen with just light. It also is why if you ever kind of are waiting for a train and you listen to it as the train is approaching you, then the wavelength of the sound is compressed, and so it sounds at a higher pitch. And when it's moving away from you, then the sound sounds as a lower pitch. So there's an analog there to viewing stars, in that the wavelength can be either shorter or longer, depending on whether the star is moving towards or away from us. So if we measure the light from the star very precisely over time, then we can try to detect that characteristic Doppler shift. And so if we can do that, then we can infer or reason the existence of a planet by the Doppler shift or the radial velocity shift or signal that we can measure. So this is showing the radial velocity signal for one of the first exoplanets discovered, 51 Pegasi. So this is showing us the shift of the light from the star, which is given in meters per second over time. And we see that it has this kind of nice cyclic pattern. So the dotted lines aren't data, but they're a particular model that's fit to the observations that are given by these black dots here. And we see that the model gives us this cyclic pattern, and from that we can extract certain properties of the planet, which is that it has a mass that's roughly half that of Jupiter, and yet the orbital period is only 4.2 days. So this is what's known as a hot Jupiter, because it's a relatively large planet, but it's orbiting very close to its host star. So this wouldn't be the type of planet that is capable of supporting life as we know it. And so usually the radial velocity signal is smaller and corrupted by what's known as stellar activity, and I'll talk about what that means in a moment. And just for comparison, I'll say that the radial velocity associated with Earth, so if we can extract the effect of other planets and only look at how much the Earth causes the sun to shift, then that signal is only 0.1 meters per second. So it's 500 times smaller than that for the planet orbiting 51 Pegasi. And so to kind of sum up the underlying science of what is happening here, if we're monitoring a star So if this is us or our telescope, then as the star, in addition to revolving, in addition to the star revolving around the common center of mass of the system, something else that we have to consider is that the star itself also rotates. So it's not this fixed body in space, but rather this dynamic ball of plasma that is itself rotating. So if we could isolate particular areas of the star, we would notice that the light from certain regions of the star is shifted either to the blue part of the spectrum or the red part of the spectrum, respectively, depending on whether it's moving towards or away from us. So here, the kind of picture is that the star itself, even if it were fixed and not revolving, would still have this red or blue shift from different regions of the star. And what we see here on the right is a graphical representation of the light that's coming from the sun that would either be red shifted or blue shifted if we isolate that light from that particular region alone. So of course we can't actually do this with any star that isn't the sun because they're all far away, so they appear as point masses. And so what happens is that these red shifts or blue shifts that come from stellar rotation would typically cancel each other out when observing distant stars, except when these stars are magnetically active, meaning that they have what's termed stellar activity, such as star spots. And it happens to be the case that we believe that most stars are magnetically active. In particular, the sun is magnetically active. So what I have here on the left is a video showing a star spot as the sun rotates. So the approximate size of Earth is given by this dot here. So we can see that these are kind of relatively big spots that appear on the sun. And when there's also a cyclic period to stellar activity, so we might observe many spots on the sun. And so these spots themselves are caused when intense magnetic fields inhibit convection, causing the associated area to appear as a dark spot. So it's not necessarily scientifically valid to think about it this way, but what we can kind of imagine is that intense magnetic fields, because they inhibit convection, there's kind of pieces of light, if you will, that are kind of missing if we think about the portion of light from a star that would either have a red shift or a blue shift, leading to this either net red or blue shift. And the reason why we care about this is that it turns out that the presence of stellar activity can mimic the exact signal that we would expect to see if a planet were present. So this is a challenge for using the radial velocity method to detect stars. Yet we want to use the radial velocity method because it's not as prone to some of the challenges that the transit method is. So we don't need to have the star passing directly in front of the planet in order to detect it. We can kind of simply monitor the planet, a particular star, over time, over specific windows in time, over a longer length of time, and find a planet. We don't need to kind of continuously monitor the star, and we don't need to have a particular geometry that the planet would pass directly in front of the star. And so this is challenging because what we observe is really a combination of a signal produced by a planet plus that from stellar activity. So we observe this combined signal But what we want is the signal due only to a planet such that we can extract the properties of that planet as we did for the earlier larger planet. So we need to remove this signal that comes from stellar activity, except here we can kind of notice that the planet is inducing this kind of extra bump in the time series in the data. And so even if you don't know too much about statistics or astronomy, you can kind of look at this, and if someone tells you that what you expect to see is kind of a cyclic pattern with this extra underlying cyclic pattern, you could probably yourself kind of pick out the data that contains a planet. But this is kind of an extreme case where the planetary signal is on the order of roughly 5 meters per second. Keep in mind, the Earth would have a signal on the order of 0.1 meters per second. So what we might actually observe is data that looks like this, where this is data from a paper that I recently published with colleagues that still had a stronger signal of 0.5 meter per second. And what we needed to do was develop statistical techniques to untangle the signal from stellar activity, from star spots in particular, from that of the planet. And so I'm not going to get into a very technical discussion of the mathematics because that would require a lot of knowledge of statistics. But to use sort of an analogy, if you have any kind of voice-activated assistant, whether it's Siri or if it's Amazon Alexa, Echo Dot device in particular is what is displayed here in the lower right. The way that they kind of work is that they listen for a particular keyword or phrase. But to do this, it has to kind of be monitoring, in some sense, a space over time. And it has a listening device. And so there might be people talking, there might be a TV on in the background. So there might be kind of lots of things that are words and speech, but doesn't contain the actual word Alexa. But sometimes it might have something similar to the word Alexa. And so this might be why sometimes if you do have these devices, you'll notice it'll turn on even if you didn't want it to. So it's a challenge for the scientists at Amazon to develop statistical approaches that can disentangle the word Alexa from something that might sound very similar, and also to just know when there are people talking nearby and know that if people are talking is different than hearing a TV and so on and so forth. So what we do is similar in some sense to this problem, except it would be like if you were at a rock concert and someone was just whispering the key phrase very quietly, because the actual signal we want to find is very meager compared to that of stellar activity. So the signal for a planet is meager compared to stellar activity. So we developed this statistical method that we then hope will have applications outside of the particular astrophysical challenge for which it was developed. So another thing that I've worked on just recently, and so I'll present kind of current results that have not yet made it into the literature, deals with detection of gravitational waves. So this is a very new area of astronomy. And so what we have here is an animation of gravitational waves detected by LIGO on September 14th, 2015. So what the simulation is two black holes that were rotating around each other. And as they were rotating, they were being drawn into one another. So the black holes rotated, and when they merged, it releases this a huge amount of energy in the form of gravitational waves. And so scientists have built these detectors to detect gravitational waves. And so I should say a little bit of what gravitational waves are. And I'll preface that with saying that I'm not an astrophysicist, so I might not get the physics of it exactly correct. So I apologize to any actual physicists in the audience. But kind of loosely, we know that any body that contains mass will warp space-time. And if we have two very massive bodies, in this case, black holes, as they rotate, they're leading to ripples in space-time, similar to if you were to have drop a stone in a pond, it will lead to ripples on the surface of the water. We can think of these rotating black holes as leading to ripples in space-time. And when they merge, they release this kind of burst of gravitational waves that are stronger than usual and strong enough that we can actually detect them. So to detect gravitational waves, we've built these detectors that work in a kind of neat way, whereby they bounce a laser off of mirrors and they measure the time it takes for lasers to go down each of two perpendicular arms. And if there's a difference in the timing, then that means that there should be a very, very tiny difference in the length of each arm, the length from the source to the mirror. And this means that space-time has been compressed or expanded by the presence of these gravitational waves. So the gravitational waves have, the arms are disturbed by a gravitational wave. So I won't pretend to understand all of the engineering that goes into it. But what matters to me as a statistician is that this is a very complex experimental setup, and it's going to therefore be subject to complex statistical challenges. And so in particular, we're not building these instruments in a vacuum. So there was a proposal to build these kind of detectors in space. That is very costly. So instead, we built them on Earth in two facilities, more than two facilities, but the first two were in, I believe, Louisiana and Washington State to give some amount of checking so one can check the other. But it's easy to imagine that the lasers can be disturbed by things other than gravitational waves. So things as simple as a car driving in the distance can produce anomalous signals, and other Earth-based signals. Earth-based sources can produce signals that are due to what are then termed glitches as opposed to actual gravitational waves. So anything that could kind of disturb the ground could lead to anomalous signals. And so what we want to do is to be able to develop automated tools that can filter out real gravitational waves from so-called glitches. And so from this, we can use the tools from statistical machine learning, or if we wanted to use a term that's more in vogue now, we can say we can use tools from artificial intelligence or AI. So what I'm showing here is a figure from a paper that I'm currently working on with collaborators, in particular in undergrad from India, whose name is Shah. And so what we see here is a real gravitational wave signal, plus other signals that look more or less like that of a real gravitational wave that have been given these kind of names that depend on sort of what they look like. So I like this one here that they called koi fish because they thought it kind of looks like a koi fish. And if you had the opportunity to visit the SFU campus, you might have seen that we do have koi fish on campus. And so what we want to do is build a machine learning algorithm that can distinguish between these different classes. And to do that, we're going to use a technique called random forest that's based on what are known as decision trees. So decision trees are a class of machine learning or AI techniques that in some ways are kind of simple and intuitive, and you might already be familiar with them. And even if not, you probably use them in your day-to-day life, even if you don't know you're doing so or use it directly. So this example that I got from the tutorial given here is based on a decision tree that you might sort of intuitively follow about whether or not to play golf. And the idea behind this decision tree is that there are a number of predictors or factors that tell us about the current weather or climate, such as whether it's expected to be rainy or overcast or sunny, whether the temperature is expected to be hot, mild, or cool, whether the humidity is expected to be high or normal, whether it's supposed to be windy or not. And sort of based on these factors that in combination describe the weather, we might make a decision, yes or no, on whether to play golf. So a decision tree will kind of take this data, if you like, and create a decision tree on whether or not we should or would play golf. So we can see that if we look back at the cases when the outlook was overcast, that in these cases, we always played golf. So even though that might seem a little bit bizarre, this data is telling us that we always play golf when it's overcast. Maybe we don't particularly like this when it's really sunny or when it's really rainy. So overcast is kind of like the sweet Goldilocks zone of golf playing, if you will. If it's sunny, however, then we have to also see whether it's windy. So if it's sunny but not windy, then we are going to play golf. But if it's sunny and windy, then we won't. And similarly, if it's rainy, but the humidity is normal, maybe we will play golf. But if it's rainy and the humidity is high, then we won't play golf. So what we do to try to learn about real gravitational wave signals, as opposed to these five glitch cases, is to extract features from the images that kind of define what we're seeing. So they're not features that are as simple as the temperature being hot, mild, or cool, but they're features that have to do with the underlying morphology of these images that we can see here. And if we do that, we can build a decision tree to classify glitches versus gravitational waves. And then we can go a bit beyond that to say that if we randomize these trees, and by randomize, I meaning instead of using all the data, we'll use a random selection of the observations called a bootstrap sample, where we're randomly selecting and replacing the observations and randomly selecting a subset of the features to potentially split on at each node, as we see here. So here we're splitting on outlook to start with. And then if the outlook is sunny, then we're splitting on windy. So instead, if we select only a subset of the features, then this is going to randomize our trees. And there's theory that shows us that this will lead to better predictive performance. So a random forest, because it's an ensemble of individual trees, so we'll use many, many, many individual decision trees, is a powerful machine learning techniques that has various applications in astrostatistics and in many other fields beyond what I'm discussing here. And in particular, I can discuss another application within astronomy, specifically solar physics, where we can also use decision trees and random forest. So as I mentioned before, many stars, and in particular the sun, are magnetically active. And the fact that the sun is magnetically active means that it can influence the Earth and near-Earth space through what's known as space weather. And so sunspots, which I already talked about earlier, are also associated with energetic bursts known as solar flares and coronal mass ejections. And that's because sunspots are associated with the sun's magnetic field, as I already mentioned. And we can see the magnetic field traced out through these loops here. And when these field lines become particularly complex, they can actually break and reconnect. And when they do so, they release bursts of charged particles. And so on Earth and in near-Earth space, in the form of satellites, we have a lot of technological infrastructure. So when we have such bursts, such as solar flares or coronal mass ejections, the particles that are ejected towards the Earth can actually damage our technology. And although we haven't seen a very powerful burst in a few hundred years, so well before we had such advanced technology, we know that the sun is capable of powerful bursts that can cause what has been estimated at up to $2 trillion worth of damage, depending on how it impacts the atmosphere. So we're interested in kind of learning about sunspots and the types of sunspots in particular in order to better understand and predict when these bursts might occur. So we can look at multiple images of the sun, in particular, the sun in white light, so how it would appear if we could look at it. So don't look at the sun. I hope I don't have to say that, but I should probably anyways. Don't look at the sun, but if you were to project the light onto a piece of paper, as you might have done in grade school, you can actually see sunspots and trace them out. In fact, this is how Galileo and others after him were to recorded observations of sunspots. We can also measure the magnetic field at the sunspots to determine its complexity. So white regions here show a magnetic field that's pointed inwards, and the black regions show a magnetic field that's pointed outwards. And so we can classify sunspots into 4 different classes based on the complexity of the magnetic fields. And what you're seeing here is that there's kind of a similar case to what we saw earlier with gravitational waves, where we can take something that has a 2-dimensional representation, hence as it appears like an image, and try to classify it using AI techniques. So in the interest of time, I won't talk about too much about what the different types of sunspots are, but rather to say that they go from kind of simple complexity to high complexity, and the high complexity sunspots are the ones that are in particular associated with solar flares and coronal mass ejections. And if we extract features, then there's sort of a natural decision tree that develops, where if the spot is unipolar, if it has one observable pole, then it's what's known as an alpha sunspot. If there's a simple line that divides the 2 poles, so those white and black regions that I pointed to on the magnetogram, then it's beta or more complex. And so this leads to a natural kind of decision tree But the statistical challenge here is that we need to somehow quantify complexity in images. And so this is useful beyond just images of the sun. So I'll kind of wrap up with this final brief example so that I can leave some time for questions, which comes from cosmology. So a brief history of the universe can be summarized as 13.77 billion years ago, there was the Big Bang, followed by a period of inflation where the universe kind of expanded quickly. And then over time, we saw increasing complexity in terms of the development of galaxies and planets and so on and so forth. And we've also seen the universe continue to expand. And recently, we've observed that expansion appears to be accelerating, meaning that the rate of expansion is increasing. And so there are cosmological models, so scientific models that predict what the future evolution and history of the universe will be based on data that we can observe. And so in particular, it's useful to observe what are known as type 1a supernova explosions. And these are thought to occur in one of a couple of ways, but one of the most prominent models is that we have a particular star known as a white dwarf that's slowly accreting matter from a companion binary star. And when enough matter is accreted, it passes a certain threshold, such as the star, the outward force of that's in the core of the star can't contain its mass anymore, and it explodes in a very typical or regular way that we can measure and then therefore use to predict the distance to that particular event. So this is really helpful because it lets us learn the distances to different objects in the universe. And so these type 1a supernovae act as something of a distance ladder, as the term is known. And they have a very particular brightness curve over time. So a particular time series that is often has errors and is unevenly spaced, to bring it back to what we discussed at the beginning about the history of astrostatistics. But if we could observe it exactly over time, we would see a very particular curve and we would know, okay, this is a type 1a supernovae. But there are different types of supernovae that have similar types of light curves as they're known. And so if we observe these with error, then determining what type it is a challenge. And there are other objects for which we want to measure the brightness over time. As we saw earlier, we could just be measuring particular stars and get light curves that have some variability due to the presence of an exoplanet. So learning which of these curves, these colored lines that we see here, correspond to the particular type of supernovae that we're interested in is challenging. And one reason why it's challenging is that newer observatories, such as the Rubin Observatory being built, are going to conduct deep surveys of the sky and produce kind of just mind-boggling amounts of data. So 500 petabytes of data over time, which is a vast amount. And it's also going to be looking further back in time, as well as other observatories from the diagram I showed you at the very beginning. So you might know that, I'll skip over this trivia question for now, that as we look further back in time, that we're looking further into space is the same as looking further back in time. And the types of objects that were present, the structure of the universe further back in time is different than it is today. And so this means that our future data sets, for one reason or another, will collect data that is different. The population of the data is different than the current data that we have. And this is a challenge for machine learning and AI, because there's always this assumption that we can use the data that we have to learn about future data. And when that assumption isn't true, then it can lead to challenges. And so this is known as something in statistics called covariate or population shift. And so for a non-astronomy example, you can imagine trying to predict the outcome of an election using polling data. And so the poll might rely on people answering their phones, whereas millennials or younger generations, and I count myself as a millennial, I would rather kind of hit my head on my desk repeatedly than have to talk to someone on the phone. And so this means that the sample of people that you're using to make a prediction, in this case, the outcome of an election, might not be the same as the sample of likely voters who are actually going to vote in the election. And if you know anything about the history of recent elections, particularly in the United States, where I'm from, you might know that polling has been kind of inaccurate. And one reason suggested for this is due to this kind of population or covariate shift. So one thing that I'm working on now with students is to develop the techniques to kind of correct for the that shift, that bias that's introduced by using a particular set of data to train our algorithms that might be different than the data that we want to eventually predict using these algorithms. So in the interest of time, I'll skip over my last application, but just kind of say that if you find any of this interesting, or even if you just have an interest in astronomy besides statistics or astrostatistics, then there's a number of citizen science projects that you can get involved in. And so many astrostats projects rely on training data that comes from actual individuals to say, okay, this particular thing I'm looking at is a gravitational wave and not a glitch, or a particular type of sunspot or a particular type of galaxy. We need to have some data to try to learn from, and that doesn't happen in a vacuum. So we're very thankful to the citizen scientists out there. And so this is an easy way of getting involved in something that has real scientific merit if you are interested. And I'll end by saying thank you very much for coming to this talk, and see if there are any questions.
All right. Well, thank you so much, David. At this point, I invite people in the room to type their questions. We do have a few questions that came in, and I invite you to keep typing your questions. I'll spend the next 10 minutes going through some of them. And the first question, I think, pertains to that graph where you show the orbital period of the exoplanets. And we have an attendee who comments that he roughly sees 3 clumps in the scatter between the planet mass and the orbital period for exoplanets. Is there theory behind why this is the case?
So I'll flip back to that plot. This was early on.
Yep.
I think this was one of the first plots.
Yes, I think this is it. Yeah.
So I'm guessing that the 3 clumps are here. That is an excellent question that I don't know the answer to. My suspicion is that might not have to do with any theory as to like planets just kind of not forming in these particular regions, but just it's my guess, and I'm not an observational astronomer, so if there are any of the audience, you might disagree with me. I have a feeling that it has to do with how the observation schedule was designed more so than any properties of the planet. So if you're observing a particular patch of the sky that contains certain stars at certain regular intervals, you would only be able to detect planets that have an orbital period that kind of is a factor of those intervals. So I would guess that that could be part of the reason. And most of these planets were discovered by Kepler, but not all of them. So some of them might have come from particular instruments looking at that would work better or worse in certain parts of parameter space. But I will check with my collaborators who are much more knowledgeable about this than I am.
Mhm. All right. Well, thank you. Let me proceed with the next question. What percentage of this huge body of existing astrophysical data has actually been subjected to any detailed analysis? And how much knowledge is therefore still hidden in the data archives?
So that is also a very excellent question. I don't know that I can estimate what percentage of the data has been any kind of subject to detailed analysis. And there's also, you can imagine that a particular data set could be analyzed in one of a number of different ways to try to probe different scientific questions. So I know that NASA and I imagine the National Science Foundation and probably NSERC have particular grants if a researcher or a research team says that I want to use this existing data to try to answer these questions that have not been asked and answered before, or I think I have or can develop a methodology that would use existing data to answer specific questions. And I'll say that we might want to think that it would be great if science had all the funding that we could ever hope for, but the real world being what it is, funding agencies kind of probably like it if you can say, hey, I can do cool science using data that already exists versus I would like to build a billion-dollar instrument to do cool science with data that might not exist. So as a statistician, a joke I sometimes make, I can't remember, I probably haven't actually been bold enough to put this in a grant proposal, but I would be bold enough to say it in a presentation, in particular to other statisticians, is that sometimes maybe if we can better utilize existing data by developing statistical methods that are tailored to the specific challenges and complexities of the data at hand, then we can save the community and the funding agency a decent chunk of change over having to develop instrumentation to kind of gather more precise and accurate data. So I won't say that maybe I should be paid a lot more money than I really am, but I'm saying that one could make that argument, maybe. I can't tell if I'm still on camera, so I'm kind of winking here. So that's tongue in cheek. If anyone here is from SFU and is actually involved in these discussions, I'm not saying, actually saying that.
All right, thanks, David. Next question. In the case of using the wobble method to detect exoplanets, are methods such as Kalman filters useful to separate the signal from the noise?
So people have used a variety of methods. I think that some people have applied Kalman filters. If you know of Kalman filters, then I can probably be a little bit technical and say that what we developed is a multivariate Gaussian process technique to try to model, simultaneously model both the stellar activity signal and the planetary signal. And we use dimension reduction techniques, such as principal component analysis and diffusion maps to extract kind of summaries of stellar activity and the corrupted radial velocity. So I said that we want to disentangle the two signals, but really we sort of take the opposite approach of jointly modeling the entangled signal to try to infer the existence of a planet given the signal. So I can point you towards or if you kind of Google my name, you'll probably find this paper on multivariate Gaussian process models for modeling stellar activity.
Mhm.
But all the other common signal processing techniques have been applied with some success.
Great. Next question, how did you come to decide to use a decision tree as the ML model?
Well, so for the solar physics application, and I apologize, I didn't have quite enough time to describe the kind of underlying science per se, but the way that sunspots are classified, and maybe I can kind of quickly go through that now. You can imagine that sunspots actually kind of lie along the complexity of the magnetic field associated with sunspots, I should say, really lie along a spectrum of complexity. But because the classification scheme was developed in the early 1900s, when the techniques for observing sunspots were much less advanced than they are now, scientists or solar physicists kind of looked at them and said that they seem to fall kind of in four broad categories. So the first category they termed alpha. And in looking at both magnetograms and white light, we can see that it looks like there's kind of like a single spot that is well-defined and is associated with just one magnetic polarity. So if you kind of imagine the magnetic field in your head, you can think of it as kind of like a fountain that's shooting, kind of coming out of the sun. The magnetic field lines would kind of like shoot out like water coming out of a fountain. And you saw that a little bit, and you can kind of still see it in the figure that's beyond here, where the magnetic field lines kind of have this sort of fountain-like structure. The next class is a little bit more complex. When you observe both magnetic fields, which is why we need to look at the magnetograms, but you can imagine drawing a simple vertical line that easily splits both polarities. The next, beta gamma, is when you have two polarities, but there isn't as simple of a division between the two polarities. And the final class is where there are multiple polarities contained within a single penumbra. So the umbra and penumbra of sunspots are, if you imagine kind of like a sunny side up egg, then the umbrae are the dark spots that we observe. That's kind of like the yolk of the egg, and the penumbra is the lighter region that surrounds it. That's like the egg whites, if you will. So if we can look at a single spot and see that it has umbrae of different polarity within a penumbra, then that would be a beta gamma delta. And so that kind of leads itself to a natural decision tree classification, where if it's unipolar, then it's automatically beta. If it's not, but there's a simple north-south division line, then it's automatically, sorry, I say if it's unipolar, it's automatically alpha. If it's not, but there's a simple division, it's automatically beta. If it's not, but there's a delta spot, then it's a beta gamma delta, else it's a beta gamma. So that's already a natural decision tree. And so what we were doing is trying to extract features that captured the scientific intuition that said that, okay, these are the important features that we see in these images that tell us that this sunspot is different than this sunspot because as we go from alpha to beta gamma to beta gamma delta, we kind of increase the likelihood of having a solar flare or coronal mass ejection. So that was kind of natural. And one of the ways that we wanted to do this in an automated way, in addition to just the fact that modern observatories, such as the Solar Dynamics Observatory, are generating a terabyte of data per day. So lots and lots of images, one every few seconds, as opposed to one per day, is just that it makes our science more reproducible because even solar physicists who are experts and trained in this sometimes disagree about a particular class. So here, I forget whether this is beta gamma or beta gamma delta. But the point is, when I showed this to two solar physicists, they said, one said beta gamma, one said beta gamma delta, because it's unclear whether this slightly darker pixel is really an umbra or not. So there was a kind of a natural reason to do so for this example and for the gravitational waves example. Something else that people have tried are something termed convolutional neural networks. So this is a new technique that has found a lot of use where you have where you're working with images. So something I didn't say is that what we're doing, so there's a kind of a data science analysis pipeline that's applied to every observation that comes into LIGO. So it has some kind of pre-filtering that is done using things like convolutional neural networks, but they've tuned the algorithms such that we're kind of more concerned about missing a gravitational wave than we are about accidentally letting a glitch in. But then in the course of running it through analysis pipeline, we extract other features, scientific features of the signals. And from those features, we can construct this random forest classifier that further kind of separates out the true signals from the glitches before we kind of continue to send it through the pipeline to further downstream analysis. So we use a random forest because we're not working directly with the images, but rather with numerical features derived from the images. We could have used other techniques such as gradient boosting machines, but we were finding that we were having quite good success already with the random forest. And random forests have some nice properties in that, well, one, we can explain individual decision trees, but they can also tell us something about variable importance. And that was sort of useful to us because these variables, the ones that we're using for classification, also have real scientific meaning and value.
Thank you. That's quite fascinating. I'll end with this last question, David, if you don't mind.
Sure, of course.
AI machine learning is very popular now, as seen in your examples. May we forget about old statistical techniques like multivariate analysis? What are older statistical methods good for?
Well, so there's kind of a joke in the statistics community that if we develop a statistics method and wait a few decades, then machine learning and AI will rediscover it and give it a much cooler name. So some AI and machine learning techniques are kind of based on older statistical techniques. So I don't make as much of a distinction between the two fields. Like if you're doing logistic regression and principal component analysis, some people might say that they're doing machine learning, even though these are much older statistical techniques that have been around for a while. I think that, but to kind of maybe be a little more fair and answer the question that you posed, older and more traditional statistical techniques certainly still have their place depending on the application at hand. So for me, the difference between kind of AI and what I might call statistical machine learning depends on whether we're interested in sort of pure prediction, where say we want to just classify whether an email is spam or not. We might not care that much about the probability of it or understand why the algorithm is making the decisions it does. We just want to sort it into our inbox or into our spam box and not have to think about it. But statistics is a lot better for, in my opinion anyways, I don't mean to denigrate anyone who might be a machine learning practitioner, where the quantification of uncertainty is paramount. So particularly for what might be called more astrophysics proper, we care not only about learning about the values of unknown model parameters, but also learning about their uncertainties. And so more often than actually using machine learning, I tend to use what are called Bayesian statistical methods, because it gives us a framework for quantifying our uncertainty. So that's used in all of the applications that I've mentioned here, even if I don't talk about it. So for example, here where I was talking about classifying type 1a supernovae versus other types of variable objects that produce variable light curves, the reason why we do that is that we want to then take that data and use it to fit cosmological models to learn something about the parameters that tell us about the history and evolution of the universe. And so that then involves more traditional statistical techniques, but we can also think about kind of developing new techniques for the fact that we have this contaminated data set. And that'll be useful for other areas as well. So in fact, for this project, we drew on techniques from causal inference. So you could think about like clinical trials and other areas where you might have one group that are the people in which you apply a certain treatment to, and another group that's a control group, and they're not exactly the same in their characteristics. So one of the examples that I didn't talk about was the very last one, which deals with computer models in stellar evolution. And I didn't talk about it because it doesn't have as straightforward of kind of like a story to tell. But loosely, I can say that the way that stars form and evolve over time are dictated by kind of complex mathematical equations. So if you are a mathematician, and it seems like there's at least some of you in the audience, there are a couple of differential equations, and we can't solve them analytically, but we can write computer code to kind of run them and evaluate them. But what we can't do is run the model very fast in real time, but we can run it a finite number of times. And my job is then as a statistician is to come up with methods that are going to combine real observed data with a few runs of these computer models to let us learn about the parameters of those models given observed data, where we need to account for different sources of uncertainty that from the actual measurement errors that we have in our observations, plus the fact that we're only running our computer models a fixed number of times, and we are doing something that's akin to fancy interpolation the other times, and then maybe even the fact that computers work with finite precision, and so there's a little bit of extra uncertainty there as well. So as a statistician, I spend a lot of time thinking about uncertainty and how to incorporate that when we're trying to do science and learn about science. So I think that there's still a lot of work to be done on sort of marrying older traditional statistics concepts with kind of newer, maybe some people might say like kind of like hotter topics from machine learning. And that's really what I was doing on that supernova application. I was taking old ideas from statistics from the 70s or even earlier, such as propensity scores, and showing how these can be used in a modern machine learning context. So I hope that that sufficiently that answers your question, but this is certainly something that I'm happy to chat about sometime in the future.
Yep, quite inspiring work, David. And thank you so much. With that, I end tonight's session, but I would like to take time to read this last comment because I think it's a perfect way of ending tonight's event. We have someone in the room who says, "What an amazing presentation. I wish I was still in school so I could take one of your classes. Absolutely excellent. I hope you'll present again to the public." So with that, I'd like to thank you, David, for sharing your research with us. And I'd like to I have a colleague at the back end helping us with the tech support for these webinars. Thank you so much for always assisting us. And of course, thank you to all those in the attendee room. Thank you for taking the time and spending this Café Scientifique session with us. We hope to see you again in our next discussions in 2023, and you will receive more information about the next series. So thank you so much for spending tonight with us, and we hope to see you next year. Take good care, everyone, and enjoy the rest of your evening. Thanks, David.
Yes, thank you very much, and thank you for that kind comment at the end. And I hope very much to present sometime in the future. Thank you.
All right. Well, thank you, everyone. Bye for now.